I've been building ant-weight combat robots for a very long time, but throughout the years, these tiny machines of destruction have had one major weakness. They break. Yes, I know, they're combat robots. Being annihilated in spectacular fashion comes with the territory, but I believe with the help of modern technology, new materials, and innovative design, I finally have the skills to engineer an unbreakable combat robot. And I'm not just talking about something that takes hits. Oh no, this thing is going to dish out the damage. Let's get started. This is Nyant, a 150-gram ant-weight combat robot I built way back in 2011. It was a ferocious vertical spinner with almost half of its weight allocated to that big weapon disc, and as such had armor consisting of zip ties and a bit of gaffer tape. I loved this robot. It hit hard, was fun to drive, and absolutely chaotic in the arena as it bounced around trying to land back on its wheels. But after almost 14 years of robot combat evolution, there is no way that something like this would be competitive today. So here's the plan. I want to reimagine Nyant. I want it to hit hard, take hits, and most importantly, never stop spinning. And we'll be starting with that big vertical weapon. If you look closely, you notice that Nyant's weapon is actually a steel ring pressed around a brushless outrunner motor. These motors are designed for quadcopters and remote control aircraft and are phenomenally powerful for their size and weight. But as you can imagine, they don't take too kindly to being smacked around by large spinning metal weapons. So why do it this way? Well, because it's so easy. You get a motor, you get a blade, a metal ruler works great, and just bolt it on and you're good to go. And with this approach, you do get a few fights out of them before they die, but inevitably a magnet will shatter, the shafts bend, or the entire bell of the motor gets ripped clean off. No weapon, no win. I've tried several things to try and extend the life of these motors, such as supporting the output with a bearing or mounting them into a shock-absorbing TPU frame, but at the end of the day, they just weren't designed for this kind of abuse. In larger weight classes, it makes a lot of sense to decouple the motor entirely from the spinning mass through something like a belt, but at this scale, we need to do something pretty wild. Enter the hub motor. A hub motor essentially integrates the motor into the wheel or hub of whatever you're trying to drive. It's a mechanically simple and robust approach to powered movement. For example, the heavyweight BattleBot Deathroll uses hub motors for its wheels to get around the arena. There's no external motors, belts, or gears to worry about. It sounds like the perfect solution, so why doesn't everyone do it? Well, naturally, nothing off the shelf exists, so I'm gonna have to make it myself. And this is the plan. I've got these 1408 size brushless motors, which I'm going to use as donor motors for the project. Here's a cutaway showing how they work. In the middle is the stator. This is a stack of steel plates with 3 separate copper wire lengths wrapped around poles. Rotating around this is the aptly named rotor, which has high strength neodymium magnets glued in a special pattern of north and south pole alignment. There's a lot more to it than that, but my hub motor will work in exactly the same way. I'm just changing the elements around to battle harden it for use. With the existing motor, there is a 1.5mm diameter shaft running from the aluminium base through bearings in the stator and into the rotor where it's fixed in place. This means that if I simply mounted my weapon blade around it, any large impact the weapon experiences would impart a huge bending force onto the bell of the motor, potentially cracking the fragile magnets or bending the thin faceplate. So instead, I'm going to reuse the motor parts to build this. The existing stator and motor mount remain the same, but the bearings and shaft are removed, replaced instead with a 4mm diameter steel shaft, which is fixed in place and does not rotate. The rotor is then cut free from the bell of the motor and instead held in place with a new ring which surrounds it. This part contains 2 ball bearings, which allows the assembly to spin freely while constraining the rotor around the stator as before. The weapon blade then mounts around the assembly, and that's it. There's many ways to design hub motors, but this is mine. Next is the fun part, the weapon blade. Nyant ran a steel ring with 2 small teeth on it, and it was fairly effective, but tended to have issues with bite. That's the term that combat robot builders use to describe how well a weapon blade can catch its opponent, transferring all of that kinetic energy into them and sending them flying across the arena. If you're spinning too fast or have too many weapon teeth, you're more likely to simply grind against the opponent instead of getting those big hits. So to get around that, I'm going to attempt something that looks super wacky, but should be super nasty. A single tooth weapon disc. When it comes to designing asymmetric weapon blades like this, you absolutely need to know your center of mass, because if it isn't balanced, the robot's just going to vibrate itself to death. Thankfully, it's super simple to find center of mass in Fusion. You sketch the blade up, extrude it, and then go to inspect center of mass. From here, I just tweak the sketch and keep checking back and forth until it's as balanced as possible. Next, you could apply all kinds of simulations, but with so many years of combat robotics under my belt, I know from experience that a good weapon blade needs to have a chunky tooth with enough material behind it to stop it from deflecting or shearing clean off. In the end, I landed on this incredibly chunky 8.3mm thick blade with a spinning diameter of 60mm. So I've got the hub motor and I've got the blade. Want to see a magic trick? With that, they are now one single indestructible component. But how on earth would you manufacture such a thing? PCBWay. That's how. PCBWay has been a long-term sponsor on Maker's Muse for many past robotics projects, and this time I really want to see how far I could push their manufacturing capabilities. PCBWay is well known for their PCB manufacturing services, but did you know that they also offer CNC manufacturing and 3D printing in exotic materials like titanium and tool steel? This blade is the chunkiest I've ever designed for an ant weight, so I opted to get it cut from 4140 steel as well as grade 5 titanium. You simply upload your design as a step file and a real engineer will go over your design to make sure it can actually be produced using your chosen process and material. They've also hooked me up with 20 discount codes that get you $10 off any order of $30 or more. So if you've got that special part for your project that you just can't make any other way, then why not give PCBWay a shot? There's links in the video description below. These blades are insane. I cannot describe how stoked I am to see all of that design work realized in cold, hard metal. The 4140 blades are crazy heavy compared to the titanium blades. This is because steel has a density roughly 1.8 times that of titanium, and I'm definitely going to be using them for a future project. But because I'm testing out this hub motor design for the first time, I like the robot it's going into to have some armor, so I'll be going with the lighter titanium blades this time. The first step in building the hub motor is the most daunting. We need to cut the rotor away from the bell of the motor. I used my lathe for this, but you could totally do it with a hacksaw if you're careful. We need to make sure that the magnets are kept safe and not chipped or cracked because they are incredibly fragile. Thankfully, the aluminium these motors are made from seems to be really easy to machine, so after no time at all, it popped free nice and cleanly. I gave the outside of the rotor a tiny bit of sanding to help the glue stick to it, and we're left with this ring that fits perfectly into the support ring on the blade. But first, the bearings need to be pressed into place. For my hub motor design, I went with 2 micro deep groove ball bearings that hold the 4mm diameter shaft, and believe it or not, I got these from Bamboo Lab, who now stock a huge range of mechanical components in their store. I can't believe it's taken this long for a 3D printing manufacturer to realize how useful it is to have a range of generic mechanical parts available for hobbyists alongside filament and that sort of thing, and the prices are really good too. The whole assembly needs to be perfectly concentric, so keeping the bearings centered and aligned as they're pressed into place is critical. And ideally, you'd use a press here, but instead I used my lathe again to line everything up, and I pressed them into place using the tailstock. It actually worked really, really well. And yes, I can hear the frantic typing now. Oh Angus, why didn't you just lathe up your own hub motor if you have a lathe? Trust me, I did try, but I am not a precise person, and this is a very tiny, precise part. When I attempted it myself, the bearing boards were just too sloppy, and it didn't work. The whole thing jammed up. Even if PCBWay wasn't sponsoring this video, I would be using their service anyway, because this part they made is going together like a dream. After the bearings, the rotor needs to be pressed into place, and I cleaned it up with some IPA and applied a very small amount of Loctite to stop the ring from spinning or coming free during the fights. I left it for a few hours to harden up, and bam, an indestructible ant weight weapon. Well, that's the plan anyway. But if you thought we were done, oh no. Remember, this thing has to never stop spinning. And the other half of that equation is the speed controller. Like the motors, much of the electronics we abuse in Antweights were designed for quadcopters, and those motor controllers don't appreciate coming to sudden stops or trying to start up motors while jammed against the floor. In fact, I've lost fights in the past because the motor controller got its knickers in a knot and couldn't recover from a particularly large impact, and that is unacceptable. Thankfully, there is a solution: AM32 firmware. AM32 is open source firmware for brushless motor control and has the ability to start sensorless motors like this one, with high torque and reliability. I last tried to use AM32 firmware on the featherweight spinner Obliterator, and I discovered that some of its features are a little too delicate for combat robot use, aka don't ever use sinusoidal startup in a combat robot or things go boom, but I loved the level of control it gave. So when I found these tiny AM32 speed controllers for only $10 a pop on AliExpress, I knew I had to give them a shot for my hub motor. These boards claim a rating of 40 amps. Now, is that 40 amps continuous or intermittent? I have no idea, but it should be more than enough for my use regardless. But you can't just solder it in place and call it a day. You need to program these with the perfect settings for combat robots. To change settings on an AM32 ESC, you can buy a dedicated programmer or do what I did and make one yourself using an Arduino, and it's really easy to do, if a bit fiddly. To program them, you plug the Arduino into your computer, plug the pins into data and ground, then you can connect to it through Direct Connect in the configuration software. And this is where all the magic happens. But I'll just focus on what you need for a powerful and reliable weapon. Timing advance, maxed. Motor KV, matched to the motor you're using, but roughly is fine. Startup power, very important for this application, so crank that up as well. Beep volume. The ESC can actually vibrate the motor musically to indicate different states, so increasing this helps you hear it when the bot's inside the arena. And on the left, the most important setting to uncheck is stuck rotor protection. Again, in a quadcopter, this setting makes sense. If the prop can't spin, the ESC will fall into a failsafe state and need to be reset, but we absolutely do not want this for combat robots. I want the speed controller to keep trying to spin the motor no matter what. Save your settings, and we're good to go. To safely test my settings, I wired in a bare motor, and this is the kind of response you can expect. AM32 allows for startup at very low speeds, but if you try and stop it from turning, it'll just keep trying. And this is exactly what I want to happen in the arena. If your motor just gives up entirely and starts beeping at you, then the settings didn't stick and you want to go back and try again. So now we have both sides of the equation complete, the hub motor and the speed controller. I quickly designed up this motor test stand to hold the hub motor in place for a first spin test, and well, there's no turning back now. Let's give it a whirl. I am so unbelievably stoked with how well this hub motor works, but proof is in the pudding. I need to now put it into a combat robot to test it properly. So in part 2, I'll be designing a robot around this crazy thing, using advanced 3D printing materials and design to create the most destructive and resilient Antweight robot I can. Make sure you subscribe so you don't miss it. A huge thanks to PCBWay for sponsoring this video, and I'll catch you again very shortly. Bye.